Okay, so today is the last lecture, and in this last lecture we'll describe a formalism to deal with low energy QCD, but a formalism that is nevertheless more general. The formalism of pseudo-Goldstone bosons, nonlinear sigma model, and what is known in QCD as chiral perturbation theory. So specifically, it's an application of the effective field theory methods for this low energy QCD. So we saw that when we have spontaneous symmetry breaking, Goldstone theorem says that there are Goldstone bosons for the broken symmetry direction. So for the direction in group space in which the symmetry is broken. But in a physical context, it's never or very unlikely to have an exact symmetry. So it's useful to know what happens when we have an approximate symmetry that's broken. And in that case, we say we have a pseudo-Goldstone boson. All right, so let's see what the symmetry is. Remember that the symmetry need not be a local one. So in QCD, we had 6 quarks: U, D, S, C, B, and T, up, down, strange, charge, bottom, and top. Charge, bottom, and top, the last 3, are very heavy. So they obey a different perturbation theory that will be briefly considered later, which is called heavy quark effective theory. But up, down are very light, and strange is intermediate. So one considers up and down nearly massless, and sometimes S is also included. All right. One also considers source terms for the various currents, which would mean coupling to some vectors for the vector current, axial vector for the axial vector current, a source S for a scalar current, and source P for a pseudoscalar current. So then the low energy QCD Lagrangian is the Lagrangian for the SU3 gauge field, minus or quarter F mu A squared. The massless, the Lagrangian for the massless up and down quarks, U bar gamma mu d mu U and D bar gamma mu d mu D. Perhaps also strange, massless strange, so minus S bar gamma mu d mu S. So this is massless QCD. Then the mass terms, which are considered small, but in principle could be included. And then this source term, so V mu for the vector current, Q bar gamma mu Q, A mu for the axial vector current, so Q bar gamma 5 Q, S for the scalar current, Q bar Q, and P for the pseudo scalar current, Q bar gamma 5 Q. So as we said, we'll consider mostly U and D, and we generalize to introduction of S just very quickly at the end. So we'll consider the quark column vector, Q is up-down, which is nearly massless. Now, of course, up-down is a doublet of SU2 gauge, right? But we're not considered SU2 gauge. We're not considering electroweak symmetry. So it's important to realize that then this this doublet is doublet in a different sense. Is doublet in the sense that if I consider low energy QCD and I ignore the masses of up and down, then I have a symmetry rotating U and D. So the symmetry is two versions of U2 rotating up and down. U2 left cross U2 right. So we said a few things about this in lecture 25. I'll remind you what we said later. So U2 cross U2, of course, is decomposed into SU2 left cross SU2 right and U1 left cross U1 right. So the action of this SU2 left and right part on U2 is a rotation, SU2 rotation, generated by tau A. So exponent, so this is exponent I alpha V for vector A tau A over 2, the generator of SU2. But then a part that is corresponds to a chiral symmetry, so with a gamma 5. So I gamma 5 alpha axial A tau A over 2, rotating the same U and D. So tau A are the Pauli matrices, and tau A over 2 are the generators of SU2. Then the left and right parts of Q are, of course, 1 plus minus gamma 5 over 2Q. And the left and right parts of the group element. So I wrote here SU2 left cross SU2 right, meaning that they're independent commuting left and right symmetries. But these left and right symmetries are not do not correspond to alpha V and alpha A, but rather to the combinations. So the group G left or right for SU2 left or right is exponent I alpha V plus minus alpha A, tau A left over 2, where tau A left over 2 is this 1 plus minus gamma 5 over 2 tau A. Okay. So tau A with the chiral projector 1 plus minus gamma 5 over 2. And in this case, these independent SU2s act on the quarks from the left. So quark left or right goes to G left or right times quark left or right. On the vector currents, on vector and axial currents, well, we've seen that the combination is alpha V plus minus alpha A. So correspondingly, gauge fields is also V mu plus minus A mu going into, and then the transformation is the usual transformation for a gauge field with G gauge field V mu plus minus A mu, G dagger left to right, plus or minus I d mu G left or right times G dagger left or right. And then if I consider also the scalars, the scalar currents, then scalar and pseudo-scalar currents, then of course I have also an action on something complex. So S plus IP goes to G left, S plus IP, G right. So that's why left and right, in the sense that left acts from the left and right acts from the right. on this S plus IP. So then, as I said, these left and right algebras are independent. So they commute, tau left with tau right commutes, and then they themselves obey the SU2 algebra. Okay, so that's the SU2 part. But there's also the U1 part, which of course acts similarly. So we had the action here with generator tau A over 2 for SU2, but now we have generator 1 for U1, right? So I have Q going to e to the I alpha plus I alpha tilde gamma 5 Q. The first part, the part without gamma 5, so e to the I alpha Q, that just rotates this quark doublet. This is just the, well, this is just 3 times the U1 baryon number. The reason why it's 3 times is because the baryon number of a baryon, like proton and neutron, is 1, and therefore the baryon number of a quark, up in D, which makes up N and P as UUD or UDD, is 1/3. Okay, so yeah. Note that the baryon number is conserved in QCD. There's no, in QCD, there's no, there's nothing that breaks this this symmetry. In electroweak theory, the baryon number is broken by anomalies through instantons. We saw that in lecture 25. And the reason was that chiral fermions left and right couple differently to it, and which means the anomalies do not cancel between left and right, unlike the coupling of the fermions to the SU3. So the coupling of the fermions to SU3 is symmetric with respect to left and right, and that's why the anomaly cancels. But for SU2, it doesn't. So there's an anomaly, and therefore in electroweak we have breaking of baryon symmetry, but not in QCD. On the other hand, the other U1 symmetry with I alpha gamma 5 in the exponent, I alpha tilde gamma 5 in the exponent, is an abelian global chiral symmetry. And this chiral symmetry is broken by anomalies in QCD. And this gave the solution to the U1 problem that we explained in lecture 25. U1 problem was the fact that there is this U1 and people did not see it in low energy QCD, in particle physics. And so they wondered, you know, where it is. And the solution was that, well, there's an anomaly which breaks it. Okay. Which breaks it at low energy. But this other one is not broken at low energy. It's only broken when you go to electroweak. On the other hand, also this SU2 cross left cross SU2 right, we don't see in particle physics, low energy in QCD. And the reason for that is that it is spontaneously broken to SU2 vector part, which is why we use this notation as alpha V and alpha A, vector and axial vector. So the SU2 left or SU2 right is spontaneously broken only to the vector part with I alpha V A tau A over 2. The axial vector part, on the other hand, the chiral part with e to the I alpha A tau gamma 5 tau A over 2 is spontaneously broken. So And this issue, so we it's not that we see it. In fact, we don't, theoretically, but you look at low energy QCD and you don't see this. So you know it is spontaneously broken. Well, moreover, the point is you see the Goldstone bosons associated with it. And then the specific mechanism by which it is broken, it is unknown. This is one of the most important issues of particle physics. This one of chiral symmetry breaking. So the exact mechanism, meaning we don't know the exact low energy effective action or how to calculate it and what it actually is. This action that shows spontaneous symmetry breaking. So the most we can do, given that we know it is there, is to write a phenomenological description of it. Just write something that has the right behavior of spontaneous symmetry breaking, but something that we don't know a priori that this is the low energy Lagrangian. Now, knowing that there's this spontaneous breaking of the symmetry, which, remember, it's not exact, but it's approximate because the up and down quarks have a small but non-zero mass. Then, by the Goldstone theorem, we have these pseudo-Goldstone bosons for the three generators of SU3, and which transform under the SU2 vector, which is SU2 vector, so the non-chiral part. The SU2 vector then is actually known as isospin. So this this symmetry without the chiral generator is known as isospin symmetry. And so the spontaneous broken vacua still transform under it. So there is only one candidate group of three approximately massless particles that correspond to these pseudo-Goldstone bosons, and those are the pions, pi A. Since approximately massless in particular means that the mass of the pions is much less than the scale of QCD, lambda QCD. So lambda QCD is the spontaneously generated scale for QCD in the quantum theory. So in the classical theory, the pions, in the classical theory, the states seem, the Lagrangian is massless. But then in the quantum theory, it generates a scale and generates spontaneously masses for the physical states. Now, what exactly lambda QCD is, there are various ways to define it, but we'll not try to define it here. One possible way is to say it's the scale of, is the mass of the proton and neutron, which is about the same, right? About one MeV. But anyway, the mass of the pions is sorry, I said 1 MeV, 1 GeV. But the mass of the pions is much smaller than that. It's if I remember correctly, of the order of 150 or so MeV. Well, I don't remember the exact number, but it's something between 5 and 10 smaller a factor of 5 or 10 to 10 smaller than lambda QCD. Then we note that there's the Wigner-Eckhart theorem, which says that in generic quantum mechanics, not just quantum field theory, which says that states should fall under multiplets of the full symmetry group. But however, it does not apply to spontaneous symmetry breaking. I mean, the point is, in spontaneous symmetry breaking, the vacuum is not invariant under the symmetry. Meaning, so if you act with generator Q on this vacuum, you don't get 0. So that means that the low energy states are not in the multiplet. So Wigner-Eckhart theorem is not invariant. It does not apply, so the states are not in the multiplet. So in our case, the pions are just in a state of the unbroken group SU2V, but are not in a multiplet of SU2A, which is broken. So they're only in the isospin states. Specifically, they transform in the adjoint representation, which is 3-dimensional. So pi plus, pi minus, and pi 0 transform like sigma plus, sigma minus, and sigma 3, which are the adjoint representation of SU2. Now, we said that we have spontaneous symmetry breaking for this group SU2A, but so this is part of the problem that we don't really know how to calculate things, because the only spontaneous symmetry breaking we saw was for a scalar field. And for a scalar field, well, it was easy. It was just minimize the potential and so on, and that was it. But now we have a theory with fermions and gauge fields, which is therefore much more complicated. In a vacuum by itself, if you would have a fermion and a gauge field, that would break Lorentz symmetry. So, so that's not good. So you cannot have a vacuum with a constant fermion or a constant gauge field, because that points in a direction in some sense. That's why, I mean, that's what breaking Lorentz symmetry means. So what happened instead is that you have Lorentz invariant condensates. So Lorentz condensates means bosonic condensates. So a bosonic field can have a condensate, meaning a non-zero field, right? Which is a condensation of bosonic particles. But if we have fermions, the way to form a boson is by having 2 fermions. So we have to have fermions forming condensates, means composite scalars made out of a fermion and antifermion that has a vacuum expectation value, meaning a constant value for this field, the prod composite field. So the composite field is therefore Q bar Q. Moreover, it's Q bar left, Q bar right, and yet, moreover, there's in principle a different flavor index. So Q bar left I, Q bar right J. Vacuum expectation value, meaning this operator in between vacuum states. And this constant that is chosen to be minus V and diagonal in flavor index space. So minus V delta ij. Diagonal and I mean proportional to the identity in flavor space. So whether or not we have this is something that we can check in principle theoretically. So there are ways to check that in a gauge theory we do have the fermion condensate at low energy. And so we can show this for QCD, even if we don't know the exact mechanism, but I will not give that here because it's also a complicated thing to show that there is a fermion condensate. But having shown this somewhere, we write it like this. Okay. All right. So as I said, until now I described massless quark leading to massless pions from the Goldstone theorem. But in reality, they're not massless. They have a mass, which is much smaller than the mass of the hadronic states, proton and neutron, which are made of up and down quarks only, UUD or UDD. But as I also said, it's important to remember that even if I consider the exactly massless up and down quarks, which would correspond to exactly massless pions, you would still have this lambda QCD scale. So you'd still have a non-zero mass for the proton and neutron. And approximately massless quarks means that the pion mass for this pseudo-Wilson boson must be much smaller than this scale, which in turn means that the masses of the proton and neutron should be to first order independent of the mass of the pion. It's a different scale. On the other hand, the mass of the pion is related to the masses of the up and down quarks. Because if one is 0, the other one is 0 as well. And in fact, at the end of the lecture, we'll show the relation that the pion mass squared is 2 times mass of up and quark plus mass of down quarks divided by f pi squared times this VEV V, the fermion condensate VEV V. The perturbation theory that we'll obtain for the pion interactions, the interactions of the pion field, will be perturbation in momentum divided by f pi, and also perturbation theory in the pion mass that's related to the fields in this way. And this perturbation theory is known as chiral perturbation theory. Okay, so to model spontaneous symmetry breaking for this SU2 left cross SU2 right going into SU2 vector, where incidentally SU2 left cross SU2 right, SU2 is approximately, I mean, it's isomorphic to SO3 modulo Z2. And then, so in terms of generators, is isomorphic. And then SO3 cross SO3 is also isomorphic to SO4, also in terms of generators. So the spontaneous symmetry breaking can be thought of as SO4 going into SU2, or again SO3 if you want. So one way to describe this spontaneous symmetry breaking is if you define SO4 through a bifundamental action, so for SO3 cross SO3, or SU2 cross SU2, acting on the set of generators one and tau A being the Pauli matrices, which are which generate a complete state in the space of of 2 cross 2 matrices. So in the space of 2 cross 2 matrices, I have the action of SO4 bifundamental action, which means action from the left with the matrix G left, and from the right with the matrix G right dagger. So then let's define the field on which we act by this SO4 in bifundamental way. Let's define this field as a complete 2x2 matrix parameterized as follows: sigma times the identity plus I tau A times the field pi A. And the notation is not incidental, but rather pi A will be related to the pion. But for the moment, these are just a notation for some scalars, sigma and pi A. So as I said, the action is bifundamental. So I act with this G left that belongs to SU2 left from the left, and with G right dagger, where G right belongs to this SU2 right. Okay, so I have my field on which I act with SO4. Now I have to write a phenomenological action for it. I mean, the field is also phenomenological, and I write a phenomenological action for it that has to have a spontaneous symmetry breaking. So the action is a simple generalization of the Higgs Lagrangian. So I have a kinetic term that just generalizes the kinetic term for one scalar. This is -1/4 trace d mu sigma dagger. And the 1/4 is because the trace, if you have the identity part, for instance, sigma, the identity part gives a 2. The trace gives a 2. So then I get 2 divided by 4, which is 1/2. So this is just the canonical kinetic term for the scalars sigma and pi A. And then I have the generalization of the mass term and of the mass term with negative mass squared. So plus mu squared over 4 trace sigma dagger. Again, trace because this has to be invariant under symmetry. And sigma dagger. That's what corresponds to the invariant object, right? Because if I write sigma dagger, then this transforms. So sigma dagger would transform as G right sigma dagger G left dagger. So sigma dagger transforms into G left sigma dagger G left dagger. And under the trace, I can put G left dagger to the left and then annihilate G left. So this is invariant under the symmetry, and similarly the phi4 term, lambda phi4 term now becomes minus lambda over 16 trace sigma dagger squared. Okay. So this Lagrangian is called the linear sigma model. Okay, and here mu squared is positive, so I would write minus mass squared, but minus mass squared is equal to plus mu squared. Okay. Now I want to couple two external gauge fields A mu and V mu for axial vector and vector, the way we saw before. So I should consider a covariant derivative. But remember that this is, the sigma belongs to this representation of SO4, on which I act with SO4 in this bifundamental way, with G left from the right, G left on the left and G right dagger on the right. So therefore, the covariant derivative is the normal derivative, and then minus I times the left vector, which is VA plus A, V mu plus A mu from the left times sigma, and then from the right, the right part of the gauge field, so which is V mu minus A mu. So plus I sigma V mu minus A mu. Okay. So this is, so coupled to external gauge field, I just replaced the derivative, normal derivative here with a covariant derivative. Then this Lagrangian has a spontaneously broken vacuum with a VEV V, which can be found from here, as usual, mu squared over lambda, I mean square root mu squared over lambda. And so sigma then must be this VEV V plus perturbations. But I parameterize the perturbations in the following way. I have to parameterize the perturbation such that it's still invariant under SU2. It's still invariant under SU2 vector, and it's broken just the SU2 axial vector. Right? So that means that I write V plus S of X times, so the other perturbations, I write them in the form that is invariant under SU2 and the SU2 vector. So U of X, which is exponent of I tau A pi prime A divided by V. Because if I expand now for small pi prime A, I would get 1 plus tau A pi prime A over V, but this is times V, so the small fluctuations are around the vacuum are S of X and I tau A pi prime A. Okay, and the VEV of sigma is V, so that means that the VEV of S is 0. And then also expanding this potential, we will find that pi prime A are massless, because this potential is still invariant under multiplication by SU2 vector by exponent I alpha A tau A over 2, alpha V tau A over 2. And it's and so this pi prime A are identified with the pions. But by expanding this potential, I'll get a mass for S. Therefore, the S is identified with the Higgs, the massive mode. All right. Now, in the Wilsonian effective action approach, we've seen that we integrate momenta, so to Wilsonian effective action approach, we get the low energy effective action in the Wilson sense by integrating out momenta higher than some cutoff lambda. So in particular, it means that one must integrate all the fields with masses that are higher than the cutoff, since they would always, by definition, have absolute value of k greater than lambda. And this is called integrating out the massive modes in the Lagrangian. When doing that, we saw that we obtain higher dimensional operators in the Lagrangian. So the lower energy effective action in the sense of Wilson was containing an infinite series of higher order operators, but at sufficiently low energies, much smaller than the cutoff lambda, these are negligible, since they came with inverse powers of lambda. So now we integrate out all the massive modes in the Lagrangian, including the S, since this has some high mass that is defined by this mu squared over lambda, squared mu squared over lambda. And that means at low energies to 0th order, I just can drop the dependence on S. So I just put S equal to 0 in this expansion. And then if we do that, the Lagrangian becomes nonlinear. So now, if I do that, then, as I said, this potential is invariant under SU2 vector, which in particular means U of x cancels, right, in the potential, right? And so there's no potential part for U. And I put S equal to 0. So there's no potential part at all. And then I put S equal to 0. So then V is a multiplicative constant that comes out of the Lagrangian. And I'm left with this U instead of sigma. So the potential is, so the Lagrangian now is minus V squared over 4 trace d mu U dagger. So this is known as the nonlinear sigma model. Right? This is nonlinear. This is linear. And well, it does look linear, meaning quadratic in the Lagrangian, quadratic in the field. Linear refers to the equation of motion. But we have to remember that U is now an exponent of something. So U really is a unitary matrix. So it means U dagger U is equal to 1. So that's a constraint. So U is not an independent field, but it's a field that obeys a constraint. Or in terms of the original sigma, sigma dagger sigma is V squared. So it's linear in terms of a field that obeys a constraint, but once we solve that constraint, the Lagrangian is nonlinear. All right. So, okay, this was in terms of some phenomenological low energy effective action. But we want to relate to QCD. So in QCD, we had quarks that we had quarks Q left, Q right, with an index I. And we saw that they formed, in the vacuum, they formed a fermion condensate. So we had 0 Q bar left I, Q right J, 0 was equal to minus V delta U delta IJ. But now we want to study this non-trivial state, not the vacuum anymore, the state where I have the pions. So the state defined by this matrix U that has pions in it. So if I consider the fermion condensate in this pion state, right, it should give me the matrix U itself with the pions. That means, but then it also, so therefore the natural generalization, which also by dimensional reasons, if nothing else, contains the VEV V, then so the relation in this state is minus, so U q bar left I q right G U is minus V times the matrix itself, U I J. Okay. So before I wrote pi prime, right, divided by V, but now I will use a new normalization that anticipates the fact that the vacuum will be the VEV will be something that we'll call F pi, the pion decay constant. Is so U is now written as I pi a tau a divided by F pi. Okay. So now we wrote pi a instead of pi prime a, and then F pi instead of V. So plugging in back in the nonlinear sigma model, we have minus F pi squared over 4 trace du d mu u dagger. Now we can also expand in 1 over F pi, and well, more precisely, it's pi over F pi, and then we obtain this expansion. So the first order term is the canonical kinetic term, but then we have a derivative interaction. So we have a term with 4 pions, so that vertex corresponds to some 4 pion interaction. But at the vertex, we have 2 momenta divided by F pi squared. So this is a vertex that is an expansion in P over F pi. So in terms of the interaction, this is an expansion in P over F pi. In terms of the Lagrangian itself, the expansion is in the pion field divided by F pi. And then in terms of the Lagrangian itself, we have to consider also the expansion in P over F pi. So this nonlinear sigma model, it's just the first order in momenta. So it's order p squared. But one has to add derivatives. So here one has to add also derivatives at higher order. So momenta p to the 4, p to the 6, and so on. Okay. All right. Yeah, and so you see that this pion interaction is comes with p squared over f pi squared, and so from this you can do some physical calculation about the pion decay and actually obtain that the vacuum, the VEV V that we found before, is the pion decay constant f pi. Okay. Also, an observation. So more generally, we call a linear sigma model a set of n scalars with a symmetry and some canonical kinetic term. So that observation can be made explicit in the most famous example, the SON model. So that's just in terms of a scalar that's a vector, meaning a fundamental representation of SON, meaning there is just n real scalars transformed under SON. So a Lagrangian with spontaneous symmetry breaking will be a simple generalization of the above linear sigma model Lagrangian. So there are n real scalars, so minus a half d mu phi I squared. And then, so this kinetic term is invariant under SON, but then to have a potential that's invariant under SON, it has to be written in terms of phi I squared. So the mass, so I have plus mu squared over 2 phi I squared, the mass term with negative mass squared. And then for the lambda phi 4, I have minus lambda phi I squared divided by 4. And that's invariant under this rotation, SON rotation of the index I. So phi I going to Rij phi j. So before I wrote this field sigma that was a complex 2x2 matrix that contained therefore 4 real scalars, but written in a form in which I could act on with SO4 in a particular way, in a bifundamental way. But now I can write, if I write this Lagrangian for n equal to 4, for SO4 equal to SU2 cross SU2 invariance, then I act with really SO4 in this way. So the 4 scalars are now in the fundamental representation of SO4. And of course, this potential has a spontaneous broken vacuum at phi 0 I squared is mu squared of lambda as before. But the point is that now by a symmetry rotation, I can orient it along the nth direction, the 4th direction in the case of SO4. So I can orient it as phi 0 being 0 on the first n minus 1 fields and v in the nth field. So then I would write phi I, the expansions around the vacuum, as pi k in the first n minus 1 components and v plus sigma in the nth component. When I put this expansion into the Lagrangian, I get, well, the kinetic terms, canonical kinetic terms, minus a half d mu pi k squared, minus a half d mu sigma squared. Then mass terms. Well, as we know from general theory, then in this, in the direction along the VEV, that's the direction of the Higgs field. So that's something that's massive, but the other directions are massless. The other directions are Goldstone bosons. That's why we call them pi, as a generalization of pions. So there's no term of the type pi squared. There's only a term of the type sigma squared. So that's the mass, which is as usual 2 mu squared. So -1/2 2 mu squared sigma squared. And then I have the interaction terms that are written here. I will not write them. I not speak them up. Okay, so this was the linear sigma model. And now, how do we call? Now we'll go to the nonlinear sigma model. But before we do that, let me specify in what in general means a nonlinear sigma model. A nonlinear sigma model in general means, as opposed to a linear sigma model, means that I have this d mu phi I, d mu phi j, but it's multiplied not by a constant, -1/2, but by something that I would call a metric, Fij, depending on the pi's, depending on the scalars, a metric on scalar space. The most famous, well, I don't know, at least for me, the most famous example in 2 dimensions is for the world sheet of a string propagating in a general space-time, where then the phi's are coordinates of in space-time of the string, and Gij is the metric in space-time. Now, so this was the expansion of the nonlinear sigma model, of the linear sigma model. But now, with respect to this more general SON or ON linear sigma model, the associated nonlinear sigma model is when I put the Higgs to 0. Or sorry, when rather I keep I keep the field in the VEV. So I keep phi I squared equal to V squared. Or by absorbing the V, by redefining by the vacuum expectation value V, I write what looks like a linear sigma model, -1/2 G squared d mu phi tilde I, d mu phi tilde I. But then the phi tildes, these fields rescaled by the VEV of phi, obey the constraint phi tilde I squared is equal to 1. So, then this nonlinear sigma model so the corresponds to fields being on the unit sphere, and gives a phenomenological description of a system with ON symmetry spontaneously broken by a VEV, obtained by integrating out the massive mode, the Higgs or sigma in this description, so this is really the same physical picture as what we did in the description, phenomenological description in terms of SU2 cross SU2. So to obtain something of the type of the general nonlinear sigma model with metric on the field space, I just solve the constraint. So I solve the constraint of phi tilde being on the unit sphere in terms of, well, I write the pions pi 1 up to pi n minus 1 in the first n minus 1 components, and the last component is 1 is equal to 1 at linear level, but at nonlinear level is not 1. It's so at nonlinear level I have to have this relation. So by solving it, it's sigma is square root 1 minus these pi squared. So if pi is small, then this is approximately 1 minus pi squared over 2. So it has no linear terms in pi, but it has no linear terms in the fluctuations, but only quadratic terms. So this has a manifest SON symmetry that, so this has a manifest SON minus 1 symmetry. So the manifest SON symmetry has turned into a manifest SON minus 1 symmetry. So the but still, of course, the theory is still invariant. It's just we are in a spontaneously broken vacuum. So by solving the constraint, we see that this linear, apparently linear sigma model kinetic term, it's actually nonlinear in terms of the independent fields. So d mu phi tilde I squared is d mu pi squared plus this nonlinear piece pi dot d mu pi squared over 1 minus pi squared. So yeah, so then I can just expand this this denominator and obtain an infinite series in the pi fields. So in this Lagrangian, I've used fields of dimension 0 by rescaling with a vacuum Bev. And then to have the correct dimension for the Lagrangian, this coupling G is actually the Bev, and it has a dimension -1. Now, to make connection with, sorry, as you mentioned, yeah, -1, yeah. To make the connection with the chiral perturbation theory, we must take n equal to 4, so that we have SO4, that is approximately SO2 cross S, is isomorphic to SO2 cross SO2 in a joint in terms of generators, and it's spontaneously broken to SO3, so SO2 isomorphic to SO3 in terms of generators, and these act on the pions. So we start with SO4 initially manifest with, but then there's a constraint. Solving a constraint, we get Lagrangian terms of the pions with only manifest SO3, while the other SO3 is nonlinearly realized. So nonlinear realization means that the symmetry is there, because I wrote the original way of writing it was explicitly manifestly invariant under SO4, and also the constraint was SO4 invariant. But by solving it, it's manifestly invariant under SO3 only. So the remaining symmetry is non-linearly realized. It's there, but we just don't see it. So that's a common thing, general thing. So a non-linear realization of the theory is something that that has changed from a linear realization of the symmetry. A linear realization of the symmetry is what we're used to when the symmetry acts like variation of a field is proportional to the field. So that is a linear transformation. But when we have a nonlinearly realized symmetry, what this indicates is that there's a more fundamental representation that has this symmetry, linearly realized. But to obtain it, we must introduce an auxiliary field. So we must introduce an auxiliary field that when you solve it, or you must write a theory with a constraint. That's another way of saying it. So in this particular case, the auxiliary field would have been this sigma, right? So when I write it in terms of the sigma, but satisfying the constraint, right? Then I see the SO4, or in general SON, the symmetry linearly realized. Okay, but if I just use the pions, I don't see the non-linearly realized symmetry. Okay, there's another way of solving a constraint for the SO4 models, for the SO4 model. We can write the sigma model as a rotation acting on the vector 0, 0, 0, sigma. So this vector is parameterized only by the, well, vev plus the massive mode. And then the full sigma model is just a rotation that takes this vev into a general field. And if the rotation is small, so infinitesimal, then we're getting into fluctuations around the vev. Okay. So I write a rotation, but the rotation acts, these components are 0, so the rotation only acts on the fourth component, so it's only Ri4. So phi I is Ri4 acting on sigma. And then we obtain that sigma is square root of phi I squared. So replacing in the linear sigma model Lagrangian, we find the Lagrangian in terms of, so in the linear sigma model Lagrangian, which is d mu phi I squared. I find the Lagrangian in terms of sigma and Ri4, right? These are the two variables that appear in phi. So it's written as this Lagrangian for sigma, the canonical kinetic term, and the potential, so negative mass squared and sigma to the 4. And then also the interaction of sigma with these R's. Then yet a further parameterization is this complicated one here, where I write the components RA4 and R44 in terms of these vector ZA in this way. Then RAB is written in this way. The rotation, the general rotation is written in this way. And then zeta A itself is written in terms of phi A and sigma in this way. But then the Lagrangian now, so written, I still keep the sigma, but I replace then the r's by these zeta a's, is written, so here the interaction in terms of sigma is 2 sigma squared times this so-called covariant derivative of the Pi field, so d mu vector squared, where d mu vector is by definition d mu zeta vector divided by 1 plus zeta vector squared. This is a complicated parameterization, but it has some interesting behavior that then the isospin SU2 vector, which used to act, so SU2 vector corresponds to SO3, to the remaining SO3 that acts on the pions, so it acts on phi A. Therefore, so this SU2 vector acts as SO3 on these pi A's or phi A's if you want. And then phi A's correspond to zeta A. So acts a vector on zeta A as a rotation on zeta A, which means this. So the rotation in terms of vector notation is variation of zeta is alpha cross zeta. So that's a linear transformation for because SU2 vector is an unbroken group that rotates the vacuum. And for the axial vector that is broken, because delta phi goes into phi 4, which has a constant piece, and delta phi 4 goes into phi. Then from these relations, we find that the variation of this covariant derivative is the covariant derivative itself, but then times not just the parameter epsilon, but also yet another zeta. So 2 zeta cross epsilon, everything cross d mu vector. So this is now obviously nonlinear. It's so d mu itself is nonlinear, but then there's yet another. You might say, well, if I consider d mu vector as a field, then if I had just d mu, this would be a linear transformation, but I have still zeta, so that's then a nonlinear transformation. Now, the vev of the scalar sigma is v. Then integrating out fluctuation in sigma, meaning just putting sigma to its vacuum of expectation value. Then this term goes away, and this term goes away as is 0. Then sigma squared is v squared. So the only Lagrangian that we're left with is minus 2v squared d mu vector squared. And if then, moreover, I define the pions as 2v times zeta vector, I would get yet another Lagrangian for the pions, which is minus a half d mu pi dot d mu pi divided 1 plus pi squared over 4v squared, everything squared. Okay. So now we observe that we have written several Lagrangians from the pions, 3 to be more precise. We have written the first that we wrote was this one, which came from the expansion of this. So putting this here and expanding, we got this pion Lagrangian. Then we got another form, this one, which was obtained from expanding this. And now we have yet another form, which is this. Okay? So this might be a little bit confusing. So what's going on? Which is the correct Lagrangian? They're all Goldstone boson Lagrangians, meaning, and they're all 2 derivatives. So that's another point. So I said in here that chiral perturbation theory contains also p to the 4, p to the 6, and so on terms. So terms with 2. So this is only the part with 2 derivatives in the Lagrangian. There's in principle terms with 4 derivatives, 6 derivatives, and so on. But for this part with 2 derivatives, we wrote 3 independent Lagrangians, 3 different Lagrangians, and they're all Goldstone boson Lagrangians, meaning their derivatives, their interactions all involve derivatives of the pion. So if the pion's field is constant, there are no interactions. But what does it mean? Well, the first observation is that what we're doing is the Wilsonian effective action, the Wilsonian effective field theory. So in principle, we should write down the most general Lagrangian consistent with all the symmetries. And then fix the coefficients from comparison with experiments. But then we say, well, at 2 derivatives, we clearly did not write the most general Lagrangian, because we have 3 different Lagrangians that have 2 derivatives. And yet, so how do we compare with experiment? Well, the point is that there's also a possibility of doing a possibly nonlinear field redefinition that's consistent with the symmetries. And that should not change the physics. If I redefine my field such that I keep the form of I keep the canonical kinetic term, and I just redefine the interactions, then all the physics, in particular scattering amplitudes, should not change. That's a general logic, because the field is just a construct that we make. It's exact when we think about it as containing only terms linear in the in creation operators in the creation operators for the unperturbed theory, but in terms of terms nonlinear in the unperturbed theory, it's not clear. I mean, it's the simplest idea is to put that to 0, but it's not necessarily so. So that means that some field redefinition of the type, for instance, pi squared is pi divided by 1 plus pi squared. This field redefinition keeps the SON symmetry acting, well, SON minus 1, I guess, symmetry acting on the pions, right? So keeps the symmetry, and it's also it's also equal an identity at the linear level, right? So at the linear level, I just have pi prime equal to pi. It's only at nonlinear level that things differ. So such a transformation would not change the physics. That's a general rule. So by doing this, we will get all sorts of different Lagrangians. So in principle, there's a field redefinition that should take us from one to another. Then, of course, you know, one can only fix as much as we can. So, we have a finite number. Well, let's say we have a finite number of experiments. Then at low energy, then we fix a number of coefficients up to field redefinitions, right? But then that does not mean that the infinite expansion in the Lagrangian. So this is an infinite series. This is also an infinite series. And if I expand this denominator, this is also an infinite series. So that would also only fix, I mean, even thinking about nonlinear field redefinition, they'll only fix a finite number of finite number of terms. So in principle, from experiments, we will fix more. Okay. I've not described for you until now what is this f pi, the pion decay constant. So we remember it from the Tukak relation from lecture 25, which stated that the anomaly in the chiral symmetry, so d mu j mu 5a plus or minus, was equal to f pi m pi squared pi plus minus. So that was associated with the decay of a pion into photon. So equivalently, this means that the hadronic J mu 5 plus minus is f pi, not f mu, f pi, sorry. So f pi d mu pi plus minus. Because if I take another derivative, then I get d squared on pi plus minus, which is by the equation of motion, m pi squared. Then, if we are interested in the decay of the pi plus minus, which has no anomalous component, the normalization of the pion was given by the pion field in between the vacuum and the pion being equal to 1 over square root of 2 the pi mass. Would mean that the G mu 5, so by this relation would mean that G mu 5 minus in between the 0 and the vacuum and the pion would be the momentum Q mu times f pi times 1 over square root 2 m pi. That in principle, that means then that we can fix f pi from the decay of pi minus into mu minus plus anti-muon neutrino. The electroweak interaction in the form Fermi limit that gives this decay is is for psi bar mu gamma 1 plus gamma 5 psi nu mu. Yeah, here. Yeah. Times the current J rho component vector minus plus component axial vector minus with coefficient the Fermi constant over square root 2. Then after a calculation that I'll not reproduce, one finds the decay rate gamma 1 over 8 pi times m pi squared minus m mu squared over m pi squared squared times gf m mu m pi squared times this f pi of m pi squared. So the decay constant is proportional to f pi squared. J mu is proportional to pi mu from this relation. And if I put it in here, that means that there's a decay. This is a interaction for the vertex for the pion going to muon and antimuon neutrino. And then, so since the decay constant for this process is proportional to f pi squared, then experimentally we can fix f pi squared. Everything else is known. Pion mass, muon mass, G Fermi is known. So we fix f pi as being about 93 MeV. I should also say, I mean, this is a small comment that there's some convention involved in f pi. There are different conventions depending on different factors of square root 2 involved. So you will see other values of f pi in various places. So if you compare, let's say, I think Peskin-Schroeder with Weinberg and with somebody else, you'll find different conventions of what f pi is. But that just rescales this f pi by factors of square root 2. Okay. So I've told you until now what is this formalism of pseudo Goldstone bosons and the nonlinear sigma model action for chiral perturbation theory. And this was all applied to QCD, to the theory of QCD at low energy. But it must be noted that the theory itself can be applied much more generally, which is why I decided to have this lecture in a quantum field theory course. This is not a particle physics course. So you might have wondered, you know, why do I give this theory if this is just something that's specific to QCD? But it's not. This method is a priori applicable much more generally to any spontaneous symmetry breaking for any chiral symmetry. So spontaneous symmetry breaking from a group G to a subgroup H. And then the Goldstone boson parameterizes the coset G over H. So the remaining group when we take out H from G. And then the Goldstone bosons will transform linearly under under H, and non-linearly under the coset, under the remaining group, which is another way of saying we have spontaneous symmetry breaking. And also, in a physical case, we will usually have pseudo-Goldstone bosons, since we have approximate symmetry. And again, we can write the most general form allowed by symmetries, by do field redefinition and fix coefficients from experiment. Now, you might ask, well, what other theory is there? I only know about QCD. Well, this was the case until, well, this was mostly the case until a few years ago, when people started realizing that supersymmetry, if it exists in nature, it is very highly constrained. So people started looking for alternative explanations to why we have a Higgs mass that is so low as observed. Usually the Higgs mass by quantum effects, by one loop effects, would go to very high scales, close to the cutoff scales, so close to the Planck scale. So people have been looking for alternative explanations, and one of them involves, several of them, one with subsets, involves the idea of the Higgs being a composite field, being not fundamental. And so the Higgs field is then something, a low energy field of the type of the pions, if you want. So the pions in QCD were low energy fields that were composites of the quarks, of the fundamental fields, which are quark. The pions were something like Q bar Q, right? So people have been thinking about finding some fundamental theory that lives at some higher scale, for which the Higgs is an pseudo-Goldstone boson. Saying that the Higgs mass is close to zero is somewhat ludicrous, but close to zero is always what always really means is that it's much smaller than some natural scale in the theory. If that natural scale is something we have not yet observed, is very high, then the Higgs mass, even though it's well, I don't remember the exact number, but of the order of hundreds of GeV, is still small, close to zero. So so people look for these kind of theories, and there are whole lectures, courses on this. So I'll not even attempt to do it, but just to be aware that this is part of a much bigger theory. That's why I decided to talk about it in a field theory course. I could also do a trivial generalization. Instead of using SU2 for QCD, you use SU3, meaning to include the S quark as its mass is intermediate. It's still much smaller than lambda QCD, but not so smaller. It's maybe, I don't know the exact number, but I think it's of the order of a 10 or something like this. But then you can still include it together with, you can still include the strange quark together with the up and down quark as being nearly massless. So then so then instead of SU2 cross SU2, you would have SU3 cross SU3 as the low energy effective action symmetry that is spontaneously broken to the diagonal part. So then the Goldstone boson matrix would be written. So before we wrote only these components, we wrote pi 0 over square root 2 and minus pi 0 over square root 2. So these were the pions identified with sigma 3 component of SU2, and then pi plus and pi minus associated with the other diagonal. But now I can embed this SU2 into an SU3 and write the SU3 matrix to include the other Goldstone bosons that are also Q bar Q type fields, but Q bar Q now means not only up and down, but also strange. So if you look at the particle physics what kind of particles there are that involve only up and down and strange, you find there's also eta 0, K0, K plus, and K minus. Yeah, this is capital K, of course. So together you find this matrix of pseudo Goldstone bosons for chiral SU3 breaking. So these are all 8 components parameterized by the 3 pions, pi plus, pi minus, pi 0, eta 0, chi plus, K0. K0 and K0 bar, excuse me. Yes. Yeah, which one it is? Yeah, here is K0 bar, right? I don't see the bar. I didn't see the bar here, but this is K0 bar. Okay. So then there's, so up, down, and strange we have dealt with in terms of low energy QCD. But how about charm, bottom, and top quarks? Well, at low energies in QCD, charm, bottom, and top are very heavy. They have actually masses that are higher than the mass of proton and neutron, so higher than lambda QCD. So then we have, for them, we have the opposite expansion. So if up, down, and strange quarks were ultra-relativistic, meaning nearly massless, charm, bottom, and top are non-relativistic, meaning with velocities much smaller than speed of light. So in order to treat them, so we treat them as non-relativistic particles. So we write it something with Lorentz indices, but it's still non-relativistic quantum mechanics, right? So it means it's not even quantum field theory if we're looking at low energies. It's just quantum mechanics. But we write it in a formally in a Lorentz with Lorentz indices, right? So we write a quark Lagrangian that has this form q bar I d slash qi minus m q bar I qi minus the interaction with a external gauge field q bar I g a slash q qi. And then consider momenta that are non-relativistic, meaning there's an mv part, right, for velocity is much smaller than 1. And then a small ki added to it. And then the 4-vector velocity is the 4-vector velocity squares to 1, of course, which means that also I can write it as v slash squared equal to 1, v slash meaning v mu gamma mu. And so I can write projectors 1/2 1 plus minus v slash v mu gamma mu, where v mu is a 4-vector in 4-vector notation, the velocity. And then I write positive and negative chirality, quote unquote, for the fields, meaning v slash h eigenvalue +1 of v slash for h and -1 for chi. And we throw away the negative chirality, which then, since v is velocity for velocity, means negative energy states. And another way of saying it, throwing away negative energy states, is throwing away Dirac-C states, which means going to non-relativistic quantum mechanics. Okay, so then this field Q is written as exponent minus I m, the mass of the quark, v dot x times 1 plus chi plus times h plus chi, which are the small variations. And then we just throw away the chi, as we said. We're left with just h. And so correspondingly, we get the high heavy quark effective theory as in terms of just this h as sum of a j, h bar j, I v dot d, h j. And then if we want to consider the next order in the relativistic expansion, I have also this terms with 1/2mq with h bar j, hj, and then id slash squared, the term with id slash squared, and the term with vd squared with coefficients alpha and beta in general. But if considering, so either considering the parameterization invariance or considering the expansion based on the relativistic one, you find that alpha equal to 1. And then the second process doesn't contribute to physical processes and can be dropped. Okay. Until now, I only discussed the coupling, the couplings of the pions. I described a low energy effective theory for the pions. But at low energies, the pions are the only relativistic particles. But from a phenomenological perspective, it's even more interesting to describe how they couple to the nucleons that compose matter. The nucleons then are non-relativistic at low enough energies, but it's interesting to see, I mean, the thing that interests us mostly at these low energies is how this couples to these nucleons. So the free nucleon Lagrangian would be minus n bar d slash n minus the mass of the nucleon times n bar n. How would I write the Lagrangian in the interaction of this nucleon with the pions? Remember, the nucleon itself is a composite field. It's UUD or UDD for the proton and neutron. And so this is also an effective theory at low energy. It's just that this composite field is at low enough energies is non-relativistic. So I don't know a priori how to write its coupling with the pions, but I have to think about it. What about the symmetries and so on? Well, the pion has only derivative interactions. It's a pseudo Goldstone bosons. So if its interaction with the pion has to be with d mu pi. So it's d mu pi n bar n. That's there. But then I have this index mu. I have to do something with it. That means I have to put gamma mu, but there's also an index pi a. So it's gamma mu tau a. That's the only possibility. That's the only constant matrix that can keep the relativistic and isospin invariance. But then this is an axial coupling. This interaction is an axial one. So it has to have a gamma 5 as well. So we find then all of this interaction piece. And then I call then by dimensional analysis, it has to be of has to have the dimension of 1 over f pi. So I call it 1 over f pi with then a GA that is an axial vector coupling. So then this is a definition, writing this coupling as GA over f pi, partly by dimensional analysis, since f pi has dimension. But then GA also happens to be this number close to 1, so it's 1.27 from experiment. Then by partially integrating the derivative onto the nucleon and using its equation of motion, which says that d slash n is mn, I can write this so I will then get an mn times GA over f pi, right? So I'll get pi n gamma 5 tau n, right? And so this is a vertex. This is the clear vertex, and so I would call the coefficient of that, I would call g pi nn, the coupling between the pion and 2 nucleons. And that will be this GA, the m pi that I obtained from the equation of the mn that I obtained from the equation of motion of the nucleon, and divided by f pi. Then if I define the fields u, which is exponent I pi a tau a over 2 f pi, right? This is yeah, I think yeah, so I call this u like this, which is note with respect to the previous definition of capital U is square root of capital U because of this 1/2 in here. And then I define also the fields a mu as being this one, I over 2 u dagger d mu u minus u d mu u dagger, and v mu the one with plus. Then we can complete the interaction term of the nucleons with the pions by introducing this so this will be a axial vector-like object, and this will be a vector-like object. So the interaction will be correspondingly n bar v mu gamma mu n minus n bar a mu gamma mu 5 n. Yeah, I'm not sure why. Well, yeah, GA, because yeah, this is the same. This is also axial. This is also axial. So it's the same GA, but why not GV in here? I would think there should be a GV in here. Maybe I would need to think about it. Why there's one here? I would think GV should be here. Anyway, then doing a further redefinition on the nucleon, so writing the nucleon as something depending on U times redefined nucleon field N, like this. I write the Lagrangian in this form, so minus n bar d slash n minus mn n bar n with inside interaction with the pions, and then n bar gamma mu with n with coupling 1/2 GA minus 1 times this combination of the pions. Okay, so that's another way of writing the pion interaction. Okay, and finally, the last thing I want to say is about the mass terms. So in the original Lagrangian for QCD, we had some mass terms for up and down quarks. And then by using this SU2 left cross SU2 right invariance of the Lagrangian without the mass, I can rotate the mass matrix for the quarks. So Q bar I, Qj, Mij. I can rotate it to this diagonal form with mu, md, and a priori also phase e minus I theta over 2. Since then the mass term would be trace Q bar left times M Q right, tracing the flavor indices, as I said. But then we saw that in the vacuum we have the fermion condensate 0 Q bar left I Q right J 0 is equal to minus V delta Ij, whereas in the physical state U we have on the right hand side we have minus V U Ij. Okay, so in the physical state, so this is in the vacuum, but then in the physical state with pions, physical low energy state with pions, I replace the mass term. So instead of M, I will have M times U. So this is M within this is Ij, and then this Q bar left I, Q right J in the state, in the low energy state, becomes V minus V times U. So the minus cancels, and I'm left with V times U in here. And of course, this has to be real, so I have to add the dagger part. Now, if the math matrix is real itself, so I don't have this phase, then I don't need this. Then I can expand in 1 over f pi the mass matrix, because u, remember, is exponent of I pi a over f pi, I pi a tau a over f pi. So expanding in 1 over f pi, this u, and writing the first non-trivial order, I find that this first non-trivial order, this which will have trace, first non-trivial order will be the quadratic order in the expansion of the exponent, which will have trace tau a tau b, which is proportional to delta ab, and then this multiplies pi a pi b. So will be proportional with trace m pi a pi b. This quadratic, so it's over f pi squared. So it's minus v trace m pi a pi b over f pi squared. And then this is the mass term. So this coefficient equals m pi squared over 2. So then m pi squared is 2, the trace, which is mu plus md, times v over f pi squared. This is the relation between the pion mass and the mass of the up and down quarks that we advertised at the beginning of the lecture, which is known as the Gell-Mann-Oakes-Renner relation. Another observation is that sometimes, so in here I didn't write the constant piece. So in principle, in here there's a 1, which gives trace m plus m dagger, which is a constant. So sometimes it's useful to just substitute the constant, and also sometimes it's useful to forget about m and just write, instead of the trace mu, trace m times trace u. Sorry, trace m, get it out, and then you're left with trace u plus u dagger, and then substitute the constant piece. So just replace this mass term in the low energy effective action now as minus m pi squared plus times trace u plus u dagger minus 2. So this would be the mass term of the pseudo Goldstone boson. So before we load Lagrangian for the Goldstone boson, but the mass term for the pseudo Goldstone boson is in the low energy effective action for QCD is written usually like this. Okay, so this was this is exactly equal to this piece. So this is a constant that I just did not write in here. If mu is considered approximately equal to ud, which by lattice simulations they're supposed to be, that's supposed to be true. So yeah, so this is the mass term, and that finishes my discussion of pseudo Goldstone bosons, chiral symmetry, nonlinear sigma model, and general low energy QCD or low energy some other theory. And this also finishes my course. So that's the last lecture. Do you have any questions? Can somebody check that they can still hear me? Okay, good. You can still hear me, so you don't have